So you can either, I'm going to go through the Fortran version. There's a Fortran version and a C version. This is practical 2 in the tar file that you have. If you look in there, you'll see that there are 4 versions of the code in there. There's version 0, version 1, version 2, and version 3. And those are incremental steps of adding OpenACC and gradually porting the whole application to run on the GPU. So what I'm going to try and do is to go through and show you what you do in order to recreate those steps. If you want, you can try it yourself. If you'd rather just look at the reference versions, you can do that. So the code itself is a very simple benchmark. It's a 3D Poisson solver. It's next to nearest neighbor stencil. It's a simple code, and the reason we're starting with that is because we'd like to be able to port this quite quickly and show it working and show the process. But a real code is very, very complicated and has a lot of complexity that we don't really want to get into. If we want to successfully port a code, we need to know 2 things. How is data moved around between the different routines, and which routines take the most time? And for a real application, that's hard. There are tools to help you to do that, and we'll discuss these tools later. But for a simple code, we can just do it by looking at it. It's only 200 lines. We need to know how data is passed, because keeping data resident on the accelerator is the most important optimization you will make. And we also need to know which loop nests dominate the runtime, and are they suitable for an accelerator? We'll probably end up porting all of the loop nests, as we'll see, in order to get data locality, keep the data on the GPU, but we have to start somewhere, so let's start with the things that take the most time. So the first thing you would do is understand your application. And here we can do it just by inspecting the code. Then we start introducing OpenACC kernels. Then we start putting in data regions to minimize data movement. Then we go up the call tree, making the data regions larger and larger and larger, so we get less and less data movement. And only when you've done all of that, only then should you start thinking about performance tuning of kernels. I know it's exciting and everybody likes to make their kernels go faster, but it's not the biggest optimization you're going to make. So how would we start? Well, we could start by just running the code as it is. So the way we would do that is, can everybody read that? So we're in the practical directory. We would first make sure that we source to get the right modules. So if we look at the modules, we get a big list of modules, and at the bottom we see CrayPAT Accel NVIDIA 35, which is good, down the bottom here. And we also see the CrayPAT into Lagos, which tells us we're compiling for the right CPU. We're using the Cray compiler, and we're using the most recent one here that's on the system, which is 8.2.1. So those are the important things that you might check straight away. Then we would go into the practical directory, and we can choose whether we're going to use Fortran or C. I'll use Fortran here. So what we would like to do is build the code. We would like to build the original version of the code. We don't want any OpenACC, and we don't want any OpenMP. So those will build the code. The make file is translating those options into the flags that you see. So the flags that you see here are no OpenMP, no OpenACC. That's just number of threads per block. Don't worry about that. Give me some feedback from the compiler. And this is to do with the problem size that we're running for the Himeno benchmark. It's a stencil code. You can choose how big the problem size is. So this has created an executable file for me, which is here. The way I run it is I say submit, and then I name the executable file. So it says it's running in this directory, And so if I go to that directory, then the job is finished and there's a log file in there. It's also got the setup file. It's also got the executable, obviously. This is the job script. This is the compiler listing file. I've copied it there because if I decide later to look at it, to see what version of the code was running, why did I get the performance I did, it's useful to have that. It doesn't need to be there. Yes, sorry. I think I can now. I think I will do. The executable file is there, and then the log file is giving me the results. So if I cat that log file, the code is not using OpenACC, it's not using OpenMP, those are just there as a sanity check. It runs the code twice. The first time is a little calibration measurement, which we ignore. The second time it runs it, it does 100 iterations. We'll look at what the code looks like in a sec. Took this much time. It converts the time into a megaflops calculation. It's not a PAPI counter or anything like that. It's not a performance counter. It just does a sum. It does a division of calculated number of floating point operations divided by the time. And this is the residual. This is the error on the calculation. That's a checksum. That's really useful when you're doing a port because it's a way of knowing whether it worked or not. So going back in the original directory, before we go on, so we get some performance. This is probably not the same because this performance was done before and it will vary slightly. So what does the code look like? Well, the code is quite simple. It has a main program. Well, we could even look at the code. Let's talk you through it. Because I'm using the course directory, of course, none of my module things are set up. So you've got a main program. You've got a subroutine, which is for initialization, and you've got a subroutine, which does the actual stencil calculation. And you've got a module which includes the data and all the timing stuff. So if you go in the main program, it calls the initialization, writes some stuff, then it does two sets of measurements here. For each measurement, it calls the Jacobi routine with a number of iterations, with some timers around it, and the timers are converted into a performance here. And it prints that stuff out. Now, what the code does originally is it does a little calibration run. It sees how long that took, and then it works out how many iterations to do for the second time. Well, we're not going to do it that way because for testing, it's better to have a consistent number of iterations. So we've hardwired that. So then it calls it again, it times how long this takes, and gets a performance figure from that. So that was the main program. If you go into this Jacobi routine, what does it do? Well, there's an iteration loop outside. It does a fixed number of iterations. That is not a loop we want to parallelize. That is not a parallelizable loop. It's an iteration loop. There's some OpenMP in the code, which we're not talking about at the moment. There's two loop nests. The first loop nest here is the stencil. So what's happening here is it's combining lots of nearest neighbor values of this data array P with some weight factors into a temporary scalar here called S0. And that value of S0 ends up going into a temporary array here. At the same time, it's computing a residual. That's a reduction variable, a reduction sum. And that's the error. GOSA is apparently Japanese for computational error. When it's done this loop nest and finished that, it then copies that temporary array back into the original data array in a second loop nest. And then it finishes the iteration loop. So it's going to do this 100 times. So what would we do? Well, where's all the time being taken? Well, the time is obviously being taken in this big stencil. You know, we can see that. You could profile the code to prove it, but we could see that. So what we would want to do here so that's what we've seen already. And this is the structure inside. The residual value here is good because we need to check some. We need to make sure that our OpenACC is getting things correct. So how would we start? Well, what we'd do is we'd go in and we would say, parallel loop around this expensive stencil calculation. We need a reduction clause here because this value is being summed up from the values of an array. So we need to say reduction. The other clauses are optional. We don't need to say how the arrays P and whatever and work2 are moving. We don't need to do that because the compiler can do that for us automatically. We don't need to say any of the scalars are private because that happens by default in OpenACC. We can, again, you can go in and do that if you want to. The only thing we'd need to be careful of, if there was an array that was private, it's where you take, where all of the threads, all of the loop iterations are going to be contributing towards a final answer. So in this case, each thread on the GPU is going to do one loop iteration, one value of I and j and k. Some of the operations it can do on its own, and you just have scalars. But this here, indirectly, each value of I and j and k is going to give you a value of SS. But then here, the values are added up together for each loop iteration. So each thread has to make a contribution to that final number. So there does need to be a synchronization to make sure that they don't overwrite each other and that all the values get combined together. And that all the values get combined together in the right way.
So basically, when you say the reduction on GOSPN, there is a join on both the threads before proceeding the next.
Well, there may not be a join. What might happen is that there's some sort of atomic region, some sort of critical region where it says, when you get to this point, only one thread can go through this bit at a time. And the other threads must wait because I must be careful. If two of them try to add in at the same time, they may end up overwriting each other. So you have to make sure that they come in and don't overwrite each other. Reductions on GPUs are really painful. If you look at the CUDA development kit, there are huge examples of good ways to do a reduction, to sum up all the values in a way that you get the consistent answer and you do it with getting good performance on a GPU. The advantage in OpenACC is that the compiler does that for you. But you do need to say, this variable is going to have contributions from everybody, so you should make sure that they're all handled correctly and you don't lose any. If you didn't say this was a reduction variable, you would end up with wrong answers because it wouldn't put these special guards in to make sure that you didn't overwrite values. If you say it's a reduction and it's a sum reduction, the sum, so plus, it's either plus, you say plus colon this ghost variable. You can do addition and you can do subtraction. You shouldn't do multiplication. The reason is because if it's an addition operation, it knows that at the start you start with 0 and then you add values on or subtract values off. Whereas if it was a multiplication that you were doing, they should all start with the value 1. If they start with 0 and you multiply onto 0, you still have 0. So the initial value should be 1. So it's telling the compiler about the initial values and what to do at the end when it finishes and it collects all the intermediate results together. How should they be combined? So yes, if you say the wrong type of reduction variable, you will get the wrong answer, and that's a programmer error. So if we wanted, we could go in and we could say, well, this is what all the data movement would be like if we were to write it absolutely explicitly. And you could say, well, that's a good thing to do. Well, it's extra work. My advice would be to only do it if you need to do it, if the compiler gets it wrong. The reason here is that actually we're going to lose all of these very quickly because we're going to start putting data regions in. So if you do it all now, you'll do a lot of work that you'll lose later on. So I would only start putting them in explicitly when you're working with data regions, if that's what's going to happen in your code. So if we wanted to do that, what would we do? Well, if you take, let's say, take a copy of this file, and you would need to edit the lines and put in the parallel loop reduction and then the end parallel loop going around that stencil loop nest. So do you want me to type that out, or do you want me to just show you the result? Deafening silence. Well, anyway, these are the commands. What I've done here is, why not make a copy of this original file, so we've kept the original. You'd change these lines in this way. You'd build this new version, ACC, yes please. OMP, no, is automatic. That's the default. Compiler feedback is really important. Did the compiler recognize OpenACC? What data movements was it going to do? Only use the data clauses, I would say, if the compiler is overcautious. The first optimization is to remove unnecessary data movements. How did it divide the loop iterations across the compiler? So this is a very busy slide. If you look at the file that's generated from this, what you'll see is it's a listing of the code, including the directives that we added, with line numbers down the side, but there's also some stuff gone in there. It's not a compilable version of the code. It's no longer a Fortran source code, but it's put in this information. So this information is telling you about these loop nests. Outside, we've got a scalar loop, an iteration loop that's running all the way down here, not shown. This number 1 is just tracking down, saying, you know, here's a loop. I've marked that this is a loop. The fact that it's a number 1 doesn't matter. It's a number. It just means a loop that isn't parallel. Then, here, this has become an accelerator kernel. How do we know that? Because a big G has appeared here, going all the way down there. That's told us it's generated an accelerator kernel. That's a good thing. Then, if you look, there's 3 loops in the loop nest. The inner loop has got some little G's going with it. The outer loop has got some little G's going with it. The middle loop has just got a number. This is telling us how the code is, how the loop iterations are divided across threads on the GPU. This is, for these purposes, it's not so important now, but when you come to looking at performance tuning, this is crucial to know this information. After the source code with these annotations, you find some messages. So it's saying, there's one of the messages says, a loop starting at line 284 was not vectorized. That's the iteration loop. Of course there's a recurrence, it's an iteration loop. So it was not vectorized, well that's what we would expect. A region between these lines, which are the lines where we added the parallel loop directive, was placed on the accelerator. That corresponds to the big G. A loop at line 295 was partitioned across the thread blocks. If you've done CUDA programming, what's happened is it's taken these K loop iterations and it said each value of K will be done by a separate thread block. So that'll be a set of threads that goes onto one of these vector processors. The I loop, it says, was partitioned across the threads within a thread block. So within that vector processor, it's going to use these vector instructions to work out which values of I. So if you've done any CUDA programming, it's like you're reconstructing an I value for this loop nest from the thread index, and you're reconstructing the K value from the block index. If you've not done CUDA, this is all gibberish, but if you've done CUDA, you'll sort of recognize that. So each thread on the GPU is going to be doing a particular value of I and a particular value of K. The J loop is being redundantly executed. What that means is that each thread, the first thread is going to do I equals 2 and K equals 2, and it's going to do a complete J loop for I equals 2 and K equals 2. The next thread is going to be doing I equals 3 and K equals 2. And the next thread is going to be doing I equals 4 and K equals 2, and so on and so on. But each one does all the J values. So the J loop hasn't been divided up over threads. Why not? Because the compiler is trying to balance up how many threads, more threads is better, but if the threads have no work to do, that's not good either. So it's keeping the J loop complete for each thread so it has enough work to do. So this is a decision that it's making. The important thing to notice is that there are two levels of division here. Across threads within a thread block, across the threads within a thread block between thread blocks. If you don't see two levels of division, your code is not scheduling well. So that's something you should always look for. When you have a loop nest here, you should always see two lines of little g's. That's telling you that it's using the threads within a thread block, so it's using all the lanes in the vector instruction, and it's using all of the thread blocks. Well, if you had a single level of loop nest, it would divide one loop over both levels. And then in the messages below, it would say it was divided across the threads, across the thread blocks and within the threads within the thread block. But if you've got two levels of loops or more, you should see at least two sets of G's. You'd either see 2 or 3. If you only see one, you've got a problem. And we'll see examples of that. Here it has made a decision on this. We will see later how to change that. The decisions that it makes are not usually bad decisions, but you can improve it, and we'll see examples of that. Yeah, that's when it's important to use your knowledge. So these messages, you should look at these messages. There's more messages, and these are to do with data movement. So it's saying here, another message. Each message has a little code. If you type explain that code, you can get some more information. It's saying allocate memory and copy whole array P to the accelerator at line 292 and free that memory at line 319. This is like a copy in, it's telling you. So it's telling you what data movements it's chosen to make. P is used in a read-only fashion, just what we'd want. Same messages for the little weight arrays A, B, and C for some other arrays. But then we see, ignore the if not already present bit at the moment. It says, copy whole array work2 to accelerator, and then copy back, copy. Work2 is a temporary array. It's initialized in this loop nest. It should be copy out. It shouldn't be copied in at the start. It should only be copied out at the end. It's getting cautious. Why is it getting cautious? It's worried about the halo values, 1 and Imax, the halos of this work array. It's worried there's a recurrence in the iteration loop. It's being overcautious. So what you can do is you can step in and you can say, well, actually, you've done that bit wrong. So I'll put an explicit message in for that array. But for the other ones, I won't worry. So if you recompile that, then what you see now is that it tells you that it's using copy out for this array. So we could run this code. I don't think there's enough time. So if you run this code, compile and run it, the time is about the same. It doesn't change very much. It's gone up slightly because we've stopped some of the data movement. But you should always check this residual, and you should check the value is right. Every stage. Then you catch your OpenACC problems early on. If there isn't a correctness check in your code, put one in. If you can make it double precision, even better. Why is this slower? Well, there's different ways we could do this. Find out about this. We need some information. The first thing we can look at is the Cray compiler runtime commentary. If you go into the job script and you look at the job script, you'll see that there's a line in there which says export CrayACC debug equals 2, an environment variable, which is commented out. If you uncomment that and you resubmit the job, and for convenience there's a script there to just resubmit the job, you've got a practical session to do all of this, then rerun it. What happens? You see a load of messages like this, which looks like overload, but there's a lot of useful information. What you're seeing is for each loop iteration, you see a string of messages like this. At line 292 in the code, it will transfer 10 items. So it tells you which arrays it's transferring by name. That's really good. It tells you how many bytes are being transferred. That's useful as well, especially if you're trying to only transfer a small amount of an array. We'll see how later. But the answer is wrong. You can check exactly how many bytes were sent, and you can check that that's the right number of array elements. These ones here are compiler internal stuff. There's not much, you don't have any control over those. And it's telling you here it's allocating space for work 2, but it's not copying it in now because we told it not to. It tells you how much data was transferred at the end, and the answer is a lot. Then it executes the kernel, 128 threads per block, it used 126 blocks. Wait for that kernel to finish, and at the end, which arrays did it transfer back? So it brings back array work 2 here. The rest of them, it doesn't actually transfer them, it just frees that amount of memory. And you can see it tells you how much data was transferred, and the only data that's been transferred is this plus, this is essentially the residual, the reduction variable. Looking at this is really good. Don't switch it on all the time because it hits performance, but when you're trying to work out exactly where was data moving, this is really useful. The other thing you can use, if you want a quick profile, is the NVIDIA Compute Profiler. So instead of setting this environment variable in your job script, you set this one. No recompilation, same job, and run that. When it runs, it'll produce a log file. If you look at that log file, there's a header, and then for every iteration, you see a line where it tells you what it was doing, memory copies, host to device, execute a kernel, memory copy device to host. Device is GPU, host is CPU. It tells you how much time was taken to do this in microseconds. This, again, is good information. And you can already see that the kernel time here is quite small, whereas the data time is really large. So again, that's telling you on a time basis that you're spending a lot of time on data movement. It's not great because, there's thousands and thousands of these lines. It doesn't give you a view of the whole application. So what you can do instead is you can use CrayPAT, which is a profiling tool that Cray provides, that can profile not only CPU codes, but GPU codes as well. So I'll make this PDF, well, the instructions are there. I can make this PDF available with the script before the practical. You load the perf tools module, you build your code. There's an extra step, which is where you go in and you have to do what's called instrumenting the code. You have to tell it what to measure. What I'm basically doing here is I say you want to trace the code. It can trace the code or sample the code. If you've not used profilers before, it's different ways of gathering information about how the code runs. I'm using the -W option to just look at what's happening on the accelerator. You submit, this creates a new executable, which includes this extra tracing information. You run that executable, and when it completes, there's a file that's called Himeno_v99.x plus pat plus blah, 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 dot .xf. And this contains all of the information that was gathered when the code ran. If you run the pat report command on this, it produces a summary of this, and it looks something like this. There's various tables in this text summary. So table 1 is telling you that what was run and how long did it take. So the user code, what was in that? There was a main program that was run once, and it took 8% of the time. And then within the Jacobi routine, there were some data movements. There was some at line 292, there was some at line 319. There was 103 calls for this, 3 for calibration, 100 iterations, and a lot of time. 86% was spent sending data there at the start, 4% was spent sending data back at the end. Sync wait, what does that mean? This is how long the kernel took to run. Kernels run asynchronously. The CPU gives a job to the GPU says, fine, I'll get on with it, back to you. Control goes back to the CPU almost immediately. The GPU then does the work, but the synchronization comes in later, where you say, have you finished the work? Or I will wait until you've finished the work. So when you look at this profile here, you don't see kernel time, you see the time it took to wait for it to finish that job. Table 2, which is underneath table 1 in this text report, gives you a bit more detail about data movements. So here it's telling you data movements here, a kernel running here, how many megabytes were moved in total, how many times was this called, how much time was taken, and a percentage of the overall runtime. So basically 98% of our runtime is data movement. That's why the performance wasn't so good once we accelerated that kernel. Well, all that data's moving around. Every iteration, we've got all that data moving. We need to put in a data region. So what do? We go in and we say, well, we only really want to move this data once and not every iteration. So our data region goes outside the iteration loop. We have to be explicit about how data moves. P will be modified, so it'll need to be copy in and copy out, so it's copy. These are read-only, so we make them copy in. Work 2, well, from the point of view of this iteration loop, work 2 is a temporary array. It's scratch space. It's initialized here, and then it's copied back into the data array here, and then we start again. So we say it's create. No data movement at all. This is as before, this loop nest, except we'll get rid of any data clauses that we added in here, we get rid of. But there was a second loop nest here, and now this loop nest has to be on the GPU again. We have to do this work on the GPU, because that's where the data is. So even though this loop nest took no time to run, it's still got to be accelerated. So we can say parallel loop. Because it's inside the data region, all the data movement will be taken care of. But this shows you that you will end up porting a lot more of your code to the GPU than you think, because you want to make sure you keep the data on the GPU. And this is where OpenACC is good, because accelerating simple loop nests like this that take no time to run is done with a single directive. You don't have to write a CUDA kernel to do that. Yes, it would be quite a simple CUDA kernel, but you've still got to have block IDX and thread IDX and blah, 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 blah. OpenACC gets around that. So these are the exact lines that you put in. You get rid of the copy out clause that was on that stencil loop nest. We accelerate the other loop nest. We don't want to profile it at the moment, so unload that, clean, make clean, build the code, submit it. Now the performance has jumped. We were at about 2,000 and now we're at 40,000 because we've got rid of that data movement. Why is it going faster? Well, switch on this CrayPAT debug line again, rerun the job. Now we see, at the start of the data region, we see data movement, but then for each loop iteration, we'll see in a minute what we see, when the iteration loop finishes, we have one bit of data movement. But for the loop iterations, the only data transfers at the start and end are these internal variables which are to do with the reduction that we can't control. So basically, almost no data is moving now. And if you run a profile, so again, load the perftools module, build the code again, do this instrumentation line, this pat build, and run it, look at the, generate the report, and now if we look at table 1, what we see is that, of course, the runtime has gone down, but now we're seeing that the main program is 40%, and these data copies are now reduced from being sort of 90-odd%, they're down to about the 25% level. And we're actually seeing this sync wait, this kernel time is now a significant part of the profile. So we're actually spending a significant amount of our time on GPU compute, not on PCI Express transfers. And in table 2, you can see that the amount of data that's moving has come down significantly. And this is looking like a better profile. Now, as I said before, kernels launch asynchronously, so you have a sync wait. Sometimes it might be clearer if you could actually see the time assigned to the kernel rather than to the waits. The way you can do this is using a magic CCE flag, ACC model equals auto async none. You know, it's great, easy to remember this stuff. Luckily, it's in the man page. The make file can put that in for you automatically. You just tell it, you add this line to the make file and run a profile again. And when you look at the profile now, you see that the time is assigned to kernels, the two kernels, the stencil kernel and the copy kernel, rather than to sync waits. It does skew your profile slightly if you compile in this way, but it does give a clearer profile. And again, you see kernel time rather than sync wait. But we are still seeing data movements. Yes? Yes? Three, four, five? Oh, these, sorry. These are indentation levels. This is being indented in here because it's to do with the call tree. The main program calls Jacobi. Jacobi has a data region. Within the data region, there's an accelerator region. Within that accelerator region, there's a kernel. So the indentation is going kind of 1, probably there should be a 2 in there, 3, then it reaches 4, and then 4, 5, instead of having more and more of these little vertical lines, it starts putting numbers here. So it's telling you about the call tree, a little bit of your application. Host time, accelerator time, here they are generally the same because we're running with, we switched the asynchronicity off with this special flag. If you went back, you'll see here that you end up with different numbers because the host is doing the waiting, and the accelerator is doing this asynchronously, so it's a very quick launch. But we're still moving data. It's only once per call to the Jacobi routine. How can we improve it even better and spend even more of our time on compute? We go up the call tree. We go into the main program, and we put in a data region that's going to go around the Jacobi calls, and we're going to say all of these arrays are going to be copy in now, and they'll just be modified inside these calls. In fact, work 2 could be create at this point. I've said it's copy in. but that's actually overcautious. It really could be set to be create. Within the Jacobi routine, we have to change the data region. We have to, instead of saying copy in for these, we have to say present, because it's in a different routine. Use the versions that are already on the GPU. So this means that this will work, and this will work fine. What would not work, if I were to call Jacobi here, outside my data region, when I'm outside the data region, these arrays are not on the GPU, and I would get a runtime error and the code would fail. And that's a good thing, because I know that my code always has the Jacobi calls inside the data routine. If they were ever outside of the data region, something has gone badly wrong, and I want my code to fail, and not just give me a quiet wrong answer. If there are cases where actually sometimes you really will want to call this outside the data region, instead of saying present here, there's some other clauses which are copy or present, which says if it's there, use it. If it's not, copy it. And we'll talk about those a bit later. Generally, I don't find those very useful. If you understand the call tree of your code, the data regions will usually span all of the calls to a routine, and then present is the safest thing. Yes?
I might have mixed up the code by now, but this working too, isn't that the answer basically?
No, P, because the first stencil takes P and puts it into work 2. The second loop nest takes work 2 and copies it back into P.
So what is create then? It's like copy in?
No, create is make space on the accelerator.
And what about?
And no data movement. So it starts off as empty space.
So it's just like a temporary.
It's just like a temporary array, yes, yes. So what do we do? We could go further than this. I mean, we can do this, and that's fine. But we've still got this initialization routine. What would be even nicer is just port the whole application. Let's just run the whole thing on the GPU. So why don't we expand this data region further and take it so it's outside and it embraces the call to the initialization routine. Then we're going to initialize the data, all of the arrays on the GPU. So we just declare them as create, and there's no data movement at all between CPU and GPU. So to do that, of course, this means that inside initMT, we're going to have to, what we do is we move our data region to go outside the initialization call. We now say everything is just temporary space, no data movement at all. And then inside the initMT, we have to, there's 2 loop nests that initialize the array. We have to accelerate those with parallel loop, and we have to put a data region around those, an inner data region. So we're nesting data regions. You're allowed to do that. So there's a data region inside initMT which just says they're already on the GPU. So for these parallel loops inside, the data's already there. So if you actually want to do that in the code, you'd edit these line numbers. Here's an outer data region that's create and end it in the main program. Inside Jacobi, we use the present clause to say in this inner data region, the data is already on the GPU. And then in the initMT, we put a data region around the 2 loop nests, and we accelerate those 2 loop nests. So most of that is fairly, I mean, there's no, we're just accelerating loop nests. There's no particular thought has to go into those other than we should accelerate these. You're not having to worry about loop scheduling or anything like that. Unload, I mean, if this is all sequential, the last thing we did was we were doing some profiling. So make sure you unload the profiling module, build the code and run it. And when we run it now, the performance that was sort of 40,000 has gone up to 56,000. So when we ran on 1 CPU core, we were getting a performance of about, what was it? It was 2,800. Now we're getting a performance which is 56,000. So we've got a huge increase in performance. Part of that is because the GPU is faster than the CPU, but most of that is because as we went through this porting process, we got rid of data movements. Because when we did the first GPU kernel, it wasn't really much difference in performance to a CPU core. The GPU was faster, but the PCI Express was really slow to move data. So it's getting the data movements right is what brings the performance up. And you can profile this code if you want. So you profile this version. Let's switch off this asynchronicity thing so we can see the kernel time. Run the code as before, and when we look at that, now what we see is that this is without the sync wait option. 82% of our time is now on GPU processing, GPU kernels, and we're down to about 15% of our time being data movements. And when you look at what the data movements are, they are very small amounts of megabytes. These are just single scalars to do with the reduction, which you can't avoid. The remainder, so if you switch on the CrayPAT debug environment variable and you run that, what you will see is that you can see exactly what the data transfers are, and it will show you that there are just the compiler internals. Well, it wasn't a very fair comparison, was it, to compare a full GPU to one CPU core? We should compile an OpenMP version that can use more of the cores on the CPU and run that. So get the profiling switched off. Don't use anything to do with the accelerator, so unload that module now. Now make this code with OpenMP, but no OpenACC. So it's the same code that we had, that we run on the CPU now, and run it using n threads, where n is a number. And you can choose what that number is between 1 and 16. When you do that, and you look at the performance, what you'll see is obviously the CPU can do a bit better than a single core, but the performance never matches what you see for the GPU. And in fact, when you look at the overall speed up, you find that it's about 3 to 5 times. And that's the sort of figure we would expect. The GPU is of the order 5 times faster peak than the CPU, be it Interlagos, be it Sandy Bridge. And we're not going to beat that. This is a memory bandwidth bound code. Yes? Uses what, sorry? It should do. I mean, the way to see that is to look at the compiler listing file, the same as you would do with the hlist equals a, and then look at the .lst file. And that will show you which loops have been vectorized. It can do, yes, yes. Yes. So, I mean, I am sure that the OpenMP is not as tuned as it could be, and you may be able to do better. But the point is, I think about the same amount of work has gone into the OpenMP as the OpenACC. So from a developer point of view, a developer effort, it is worth using the GPU here. So we ported the whole code. There were 4 parallel loop kernels. Only one was actually significant for performance. 1 outer data region, 2 inner data regions. So that's a total of 7 directives. Profiling frequently showed us what was slowing us down. We checked correctness by looking at that residual. The first optimization is always the data movements. We did look at these kernels. We checked to see how many little g's we saw in that loop mark. Look for sensible. Don't worry about the exact details, but look to see if it's sensible. We got a sort of 20 to 40 times speed up. Depends whether you're on TERDY or DAINT as to which number you'll get there. From looking at data movements. OpenACC makes data movements a lot more easier to handle than CUDA. It's just easier to write it all. But we're going to look later on at tuning the kernel performance. We're never going to see speed-ups like that from performance tuning of OpenACC kernels. Factors of 2 are more likely. So don't waste time on kernel tuning if you've got too much data moving. So that has taken far too much time. But in a way, I'm not sorry, because I've gone through it slightly more slowly. and if you get the basics right. So I would say that we should talk about the OpenACC 2, the more features, after lunch. Would that make sense? And they do the practical now? Yes, because the practical is, you've just seen the practical. The practical is for you to go and do that yourself. And it might be better for you to do that now while it's fresh in your mind. The more features tidies up a few things, but there's nothing in there that you need to do this practical. The idea was to schedule the practical before lunch so that it gives you a bit more flexibility. You can avoid the queue by doing a bit more practical, or you can go early. You know, you can judge it. If you're bored of the practical, you can get coffee. If you're really interested, you can grab some lunch right at the end. Yes? You need this PDF right now, don't you? So why don't I just generate this one now and put it on Turdy, and then they can just pull it off? Is that the best thing to do? Yeah. Right, I'll just generate this now, because you're going to need this. In the meantime, if you go into practical, okay, so in, let's see. I've put the PDF for those slides here. So from a course directory, you should be able to copy that PDF off and then put it on your laptops. Does that make sense? There's also stuff in the README file, but if you want the kind of every command to type, or every command that I could remember that you should type within the slides, you might want to look at that file. Yes? Yes. It gets more complicated then, and then, I mean, it's kind of, it's more than just a GPU problem. That would be a problem of how would you run on a node, a CPU node with 6 gigabytes instead of 32 gigabytes. So, you know, I mean, one option is that you say, okay, if I have a parallel code, I'll run with more MPI ranks, so that, you know, the local problem size fits in 6 gigabytes is one way to do it. The other way to do it is, I mean, you can then, you may get to the point where some data movement is needed. I mean, there's different ways you can do it. You could try and, you'd have to reuse data in the GPU memory. And so either you have different data regions and you move some data in and out and do it that way. There are more sophisticated ways to do things. I mean, the trouble is, I mean, you kind of say to yourself, if I really need that much memory, you know, maybe I would be better running just with saying, there is 6 gigabytes, I want to use the GPU. I'll have to use more MPI ranks to do the problem. And that might be the sort of cleanest way to do things. But of course, you know, you pay by the node, so. Yeah. Yes, I mean, the halo exchange and this sort of thing will start to hit you because you're strong scaling. And strong scaling with the GPU is more expensive than strong scaling with just the CPU because of the PCI transfers. There are other ways to do things. There's some more sophisticated control. I mean, essentially, you can use library calls, API calls, to do anything that a data region does, and other things as well. So you could almost allocate your GPU memory as a user-managed cache and manage the transfers around to and from that cache yourself, hopefully using asynchronicity to overlap, you know, while you're computing this, get something else moving there. It's undeniably, that's a difficult thing. OpenACC can help with that, but it can't give you more memory. So, you know, you're going to have to do quite a lot of software engineering. And whether you write that in CUDA or you write that in OpenACC, there's still going to be some degree of thinking to work that out. Well, the current generation, yes, the current generations of GPUs is 6 gigabytes. I mean, you know, in the future there may be more, but there is less memory than there is in the node. You can use, you mean, well, it depends what you mean. In what's, you can, if you have, say, an MPI code, you know, the message passing type code that would run typically over multiple CPUs, each CPU can talk to its own GPU in that way. But there's not, you can't sort of, I don't think it's an easy way to sort of transparently write in a sort of global shared memory sense, you know, sort of OpenMP or UPC type view of multiple nodes of GPUs and sort of have one memory space for them all. I mean, parallel codes with MPI or Fortran coarrays or whatever that each use a GPU, each node, work very well with, you know, certain performance issues. But there's no kind of transparent way. That means you do need a domain decomposed code. This is supported within OpenACC, and there's all sorts of runtime API calls to do with selecting which device to use. Cray does not support that simply because we don't ship hardware that has that feature. But you know, the PGI compiler is a bit more flexible in what it targets. So I think in CAPS, the CAPS compiler, so they kind of implement that. I mean, Cray implements the calls. It's just they kind of return trivially because you can't select any other sort of device. There's a GPU, and there's one GPU per node. So can people read the PDF? Right. So if you want to follow all the stages and do it step by step, line by line, then I would go through the PDF. If you want to skip ahead and just run it and look at what the compiler, look at the list file, see what the performance was, then I would just kind of do make version equals 00, make version equals 01, make version equals 02, and so on, and just run those sequentially. But do that. Maybe try doing a CrayPAT profile. When you've run a job, go and edit the job script and switch on one of those environment variables and get the feedback from that. I mean, a GPU is a bit of a black box, so you know, getting information back is even more important than for the CPU. Sorry, someone had a question. I got distracted. Yep. All of the examples are running on one GPU, so it's one node, and that node has one GPU. Well, what would change is, is this an MPI code you're thinking of? So for an MPI code, you have a local problem calculation. So your array dimensions are the local size of the problem, and that's, you know, the global size divided by the number of ranks or something. And then you do, you know, your array operations locally, and then you have Halo exchange or something. You can do all of the OpenACC for the local problem stuff. There's a bit more complication with the Halo exchange, but I'm going to talk about that this afternoon. But when you were doing when one node was doing its local problem, you can do that using its local GPU, and that works fine. Yep. Yep. Yes, I've put that in. This is kind of jumping ahead slightly. This afternoon, we'll talk a little bit about performance tuning, and if you've done any CUDA programming, one of the things that you sometimes vary is the number of threads per block. Vector length is the equivalent of that. I put that clause in because if you want to use the example to do performance tuning, it's already there. But it's not necessary. The default is 128. And not that that really matters. File is translating those options into the flags that you see. So the flags that you see here are no OpenMP, no OpenACC. That's just number of threads per block, don't worry about that. Give me some feedback from the compiler, and this is to do with the problem size that we're running for the Himeno benchmark. It's a stencil code. You can choose how big the problem size is. So this has created an executable file for me, which is here. The way I run it is I say, submit, and then I name the executable file. So it says it's running in this directory, and so if I go to that directory, then the job is finished, and there's a log file in there. It's also got the setup file. It's also got the executable, obviously. This is the job script. This is the compiler listing file. I've copied it there because if I decide later to look at it, to see what version of the code was running, why did I get the performance I did, it's useful to have that. It doesn't need to be there. Yes, sorry. I think I can now. do. The executable file is there, and then the log file is giving me the results. So if I cat that log file, the code is not using OpenACC, it's not using OpenMP, those are just there as a sanity check. It runs the code twice. The first time is a little calibration measurement, which we ignore. The second time it runs it, it does 100 iterations. We'll look at what the code looks like in a sec. Took this much time. It converts the time into a megaflops calculation. It's not a PAPI counter or anything like that. It's not a performance counter. It just does a sum. It does a division of calculated number of floating point operations divided by the time. And this is the residual. This is the error on the calculation. That's a checksum. That's really useful when you're doing a port because it's a real application that's hard. You need, there are tools to help you to do that, and we discuss these tools later. But for a simple code, we can just do it by looking at it. It's only 200 lines. We need to know how data is passed because keeping data resident on the accelerator is the most important optimization you will make. And we also need to know which loop nests dominate the runtime and are they suitable for an accelerator. We'll probably end up porting all of the loop nests, as we'll see, in order to get data locality, keep the data on the GPU, but we have to start somewhere, so let's start with the things that take the most time. So the first thing you would do is understand your application. And here we can do it just by inspecting the code. Then we start introducing OpenACC kernels. Then we start putting in data regions to minimize data movement. Then we go up the call tree, making the data regions larger and larger and larger so we get less and less data movement. And only when you've done all of that, only then should you start thinking about performance tuning of kernels. I know it's exciting and everybody likes to make their kernels go faster, but it's not the biggest optimization you're going to make. So how would we start? Well, we could start by just running the code. So you can either, I'm going to go through the Fortran version. There's a Fortran version and a C version. This is practical 2 in the tar file that you have. If you look in there, you'll see that there are 4 versions of the code in there. There's version 0, version 1, version 2, and version 3. And those are incremental steps of adding OpenACC and gradually porting the whole application to run on the GPU. So what I'm going to try and do is to go through and show you what you do in order to recreate those steps. If you want, you can try it yourself. If you'd rather just look at the reference versions, you can do that. So the code itself is a very simple benchmark. It's a 3D Poisson solver. It's next to nearest neighbor stencil. It's a simple code, and the reason we're starting with that is because we'd like to be able to port this quite quickly and show it working and show the process. But a real code is very, very complicated and has a lot of complexity that we don't really want to get into. If we want to successfully port a code, we need to know 2 things. How is data moved around between the different routines, and which routines take the most time? And for a real, as it is. So the way we would do that is, can everybody read that? So we're in the practical directory. We would first make sure that we source the, to get the right modules. So if we look at the modules, we get a big list of modules, and at the bottom we see CrayPAT, Accel, NVIDIA 35, which is good, down the bottom here. And we also see the CrayPAT into Lagos, which tells us we're compiling for the right CPU. We're using the Cray compiler, and we're using the most recent one here that's on the system, which is 8.2.1. So those are the important things that you might check straight away. Then we would go into the practical directory, and we can choose whether we're going to use Fortran or C. I'll use Fortran here. So what we would like to do is build the code. We would like to build the original version of the code We don't want any OpenACC, and we don't want any OpenMP. So those will build the code. The make file